right, so we're going to talk a little bit more about KSP and solubility equilibrium. Specifically, we're going to look at how we can tell about if a solid's being formed. Okay, so this one is telling us that we have a 0.1 molar potassium carbonate, which is K2CO3 solution. And we've got some barium and silver ions, and we want to know which one is going to precipitate out first. So basically, you want to know which one is going to have the lower molar solubility for CO3. All right, so if you were to set these two up in ice tables and then plug it into your equilibrium expression, you would get x squared and 4x cubed. Then when you solved for x for both of these, you get, all right, so there you go. There are solutions. So this is the x value. And since both of the CO3s over here have a ratio of 1, then this is their actual values. So this guy has the lower value, so he's the one that's going to precipitate first. All right, now this question is telling us our concentrations of copper and lead, and then saying if we add some iodine ion to the solution, which one's going to precipitate out first, PbI2 or CuI? All right, so we basically need to solve for the I concentration. The one that needs the least amount of I to precipitate out is going to be the one that would precipitate first. So the one with the lowest I concentration. All right, so I'm just going to write the KSPs for these guys. So we got Pb2 plus, I1 minus, and that one's squared. And then we've got the KSP for copper 1 iodide. All right, so we're just setting these equal. Well, first we're plugging in our coppers and our leads. All right, so for this one, all right, so our KSP is 1.4 times 10 to the negative 8th. Our Pb2 plus is 2 times 10 to the negative 3rd. And then I'm looking for my I, so we're going to call that x, and that's going to be x squared. All right, solve for x. It'll tell me how much I need. All right, and for this side, I got 2.6 times 10 to the negative 3rd. All right, that's the concentration of I that would need to be present for that one to precipitate. Now we're going to do the same thing on the other side, but with the correct values. All right, and again, we're solving for I. It's just going to be x this time. Do some math. All right, in this x, we got 5.3 times 10 to the negative 8th. So this one is much smaller, which means that our CuI is going to precipitate out first. All right, now there is something called the common ion effect that we need to talk about. Basically, if you have an ion that is in common with your salt, it's going to mess up your equilibrium. It's going to shift it. You're going to have to look at Le Chatelier. You can also calculate this. So in this example, it wants to know what the solubility of our AgI is going to be. This is the KSP. And we're putting it in a solution that already has I in it. All right, so you need to do an ice table here. Solids don't matter. You don't have any Ag initially. Your I initially comes straight from this. Since it's attached to an Na, it's completely soluble. So we know that we have that much I minus to begin with. And then we got to gain some Ag. So we're going to do plus x, and then we got x, and then 0.5 plus x. All right, now we're going to set this equal to our KSP equation. So basically we end up with x and 0.05 plus x. All right, and then you set it up over here, times 10 to the negative 16th. All right, and that's 0.05x plus x squared. So this kind of puts you in a quadratic formula situation. You could go ahead with this, or you could remember the rule about having really small k values. So because we have a really small k value here, we can ignore anything that is added or subtracted from a normal number. So 0.05x is what we get. And then x is equal to, all right, and we get 3 times 10 to the negative 15th. That's our x concentration. And since our x, we all have 1:1:1 ratios over here, that's going to be your molar solubility for AgI when it's in a 0.05 molar NaI solution. All right. You can also predict if the system is going to precipitate based on calculating Q. Q is called solubility product here. We have previously known it as the reaction quotient. Basically, if your Q is less than your KSP, that means that you have not yet reached equilibrium. It's unsaturated. So you're going to continue to make more of the salt, so that it will not of the salt, but of the dissolved salt, the aqueous salt, the ions. If Q is equal to KSP, it's at equilibrium. This is called saturated. If Q is greater than KSP, that means you have too much stuff dissolved, so it's super saturated. So you're going to form a precipitate in this case. So the only time you're ever going to form a precipitate is when you're in a supersaturated solution. All right, so in this example, we need to look at Q in order to determine if the CeIO3 is going to precipitate. Okay, so in this case, because we are adding two different solutions together, that's gonna change our concentration because we're changing our volume here. So you need to recalculate your concentrations for both CE and IO3. So that'd be step one here. All right, so I'm going to do this by molarity equals moles over liters. So I got 4 times 10 to the negative third is equal to x over 0.75. All right, which gives me 0.003 moles of my CE. And then divide by my new volume, which is 1.05 liters. And I get a concentration for CE of 0.0029 molar. All right, that's my CE. All right, now I'm going to do the same thing except for my IO3. So molarity equals moles over liters. So 2 times 10 to the negative second is equal to x over 0.3. And I get, all right, so from moles, I got 0.006. And then divide by my liters. And my new concentration, or my actual concentration of I, is going to be 0.0057. Okay, now I need to set up my KSP equation. I can calculate Q this way, and then I can compare my Q to the K value that was given to me, and I will know if precipitation will occur. All right, so there is my KSP equation. Now I'm going to take my CE and plug it in, and I'm going to take my IO3 and plug it in, and I'm going to get my Q value, which is equal to, all right, so I got 5 times 10 to the negative 10th here. All right, looking at Q and K, you can see that Q is slightly bigger than K, which means that it's going to shift this way to decrease the Q value to where it's like K, which means that I'm going to have some precipitate form here. All right, and lastly, we're going to look at the relationship between Gibbs free energy and the equilibrium constant KSP. So again, if it's a negative delta G, that means you're very product favored. It's really going to dissolve very well. If you have a very positive delta G, it's not going to dissolve very well, and therefore you're going to have a lot of precipitant.